We're just as, let's say, pleased to see that maybe we would rule out some technologies as being infeasible for one technical or economic reason or another. In other words, to steer a clearer path into the future.
The earlier project, for example, we'd looked at microwind, and one of the things that we found by looking at microwind was that it didn't perform very well typically in urban areas.
Now, it's not to say that small wind doesn't have a role out there on the farms and the exposed sites, but I think for urban development, we've really all concluded now that this is a non-starter. Photovoltaics has actually been, perhaps unexpectedly, the success story. So thanks to government sponsorship and the FIT, we now have something like 3 gigawatts of installed photovoltaic capacity. And so far that's being done without any problems for the electrical infrastructure, which is good.
Because although solar fluctuates with the cloud cover, locally they all go up and down together. This can be quite a problem for the network operators.
Summer bank holiday on Sunday is sunny, and people left their home and went to have lunch somewhere or walks to the wood or what have you. And then in the middle of the day, there will be not very much load and there will be sun, and all these generators are going to generate, and then we will start exporting power to the system, and that would cause voltage rise effect, which is the key limiting factor for the amount of PV you can put in.
If you look at the FIT scheme, it says you use half the energy on site. This is complete rubbish. You use about 20 or 30%. And the reason is the nature of your use profile. You do not use chunks of kilowatt hours, you use a few watts, 100 watts perhaps in a day in the summer, and then 10 minutes to 2 or 3 kilowatts.
The scale of the challenge with regard to decarbonisation of heating emerged, and that didn't exist prior to this project.
At the moment, you buy your electricity from the grid, and you've got a gas boiler probably at home for your heat.
Large-scale power stations tend to be about 30, 40, 50% electrical efficiency, and the rest of the energy comes out as heat. This is just dumped into the environment via the cooling towers.
Specifically, we were looking at a couple of the microgeneration types of units, so here air source heat pumps, micro CHP units.
CHP is important because it is the combined production of both heat and electricity, so therefore you avoid some losses of having separate production.
Heat pumps have been suggested as a really useful way to decarbonise heat under the assumption that the electrical supplies are also decarbonised at the same time.
They measured their consumption at 5-minute resolution, so really a very substantial data set. We used that data set to try to understand the impact of those heat pumps on the network. So what peak load would they cause? How many new power stations do you need to serve that load? How much new transmission and distribution capacity do you need?
You buy a heat pump, it's going to take 3 kilowatts. Big one, 5 kilowatts. So again, we have a problem. You've got a steady load on a system which is designed for stochastic loads.
So if you go down this heat electrification route, again, you create a lot of load on your low voltage distribution network.
The cost would be, just in distribution networks, investment costs between 30 and 90 billion pounds.
What is the possibility of clustering microgenerators together? So rather than having a single generator, which might be a heat pump or it might be a combined heat and power plant, what would happen if we had a series of different generators?
You can actually balance that load with CHP. If you also have CHP in your low voltage distribution network, both technologies are heat led, they essentially cancel each other out and you end up with a mitigated infrastructure impact.
What can distributed generation do for the network? Well, it can put on, if we have enough of it, a few, 1 or 2 gigawatts of generation at peak load.
One of the interesting things about this idea of clustering microgenerators was that came from some of our industrial partners. That came from colleagues at HiDEF in France and at E.ON in the UK.
So actually it turned out that by making the houses very efficient, you would save at least £3,000 per house. just by avoided network and generation infrastructure. We could afford to invest at least £3,000 per house on energy efficiency and still be better off.
So this is stuff we can do today if we use it properly and we coordinate. And I think that's quite an important finding.